Hi. Okay, so I'm going to explain exercise 6 on section 12. So it's show that S is an open set if and only if each point in S is an interior point. So for the forward direction, if we let S be an open set, we want to show that every point is interior point. So we assume for contradiction, there's a point Z naught, which is not an interior point, and open sets don't have any of their boundary points. So Z naught can't is not an interior point, and it's also not a boundary point. So with boundary points in every single epsilon neighborhood, they have members from both S and the complement of S. So since Z naught is not a boundary point, then there has to be some epsilon neighborhood where the epsilon neighborhood is completely within S or completely outside of S. So this epsilon neighborhood, it can't be completely within S because then that would mean Z is an interior point. I mean Z naught is an interior point, and we said it's not an interior point. So that means that this epsilon neighborhood has to be completely outside of S. But if it was completely outside of S, that would mean that Z naught itself is outside of S. And we said Z naught was a member of S. So that's a contradiction. So that's why um, every point has to be an interior point. So now if we, for the other direction, if we just let S be a set made up of only interior points, and we want to prove that S is open. So if we assume for contradiction that S isn't open, then that means that S contains at least one boundary point. And since we said S was only made up of interior points, then that means we have a point Z naught, which is both a boundary point and an interior point. And this can't be the case because if it was an interior point, then it has a very small neighborhood where it's completely within S. But if it's a boundary point, then even that neighborhood has to have intersection with the outside. So this such a point can't exist, which means that S has to be open. I mean, there is no boundary point, so S has to be open.